Hello Amiga coders, it's time again for another tutorial. I'm Photon of ScoopX and we're going to learn how to blit stuff. We're going to use one of the custom chips in the Amiga called the Blitter, which is housed inside the Agnes chip, which is not to say that the Agnes chip is the Blitter. The Agnes chip contains, among other things, all the logic required to shuffle all the DMA in the computer to various chips. But what better chip than to house a Blitter inside, which can take priority over the CPU. How do we use the Blitter to do something interesting? Well, let's check where we were. We had filled our 1-bit plane screen buffer below the logo with iterated numeric values from 0 upwards. This generated a pattern with the CPU. Now we have something in our bit plane, that's the important thing. What if we wanted to clear the screen with the Blitter? After all, the Blitter is very much faster than the 68,000 processor. When you're nearing 68,030 speeds, that's no longer the case, and then you might want to look at various CPU routines to clear the screen. How do we go about this? Well, we know that we have some buffer pointers somewhere. We had put our little loop that fills the screen in the init routine here. I'm going to put a bookmark. Again, the goal of this series is to, at the end, produce a completed demo, complete with music and some sort of effect. Maybe it'll be a scroller. Who knows? So anyway, here's our screen, aptly named, and we fill it with increasing numeric values. After this, I'm going to show you how to clear a portion of the screen and how to think about Blitter sizes and modulos. These values are what forms a sort of a rectangle in memory, which suits your screen format. So let's see this here now. How does this work? How do you tell the Blitter to do anything? Well, the last thing you do is you write a Blitter size, a Blitter window size, and this is done by, like all other things, you poke a register in the custom chip area, and the address is hex 58, register hex 58, also called BLT size, where BLT stands for Blitter and not bacon, lettuce, tomato. We don't really know yet what the size of the rectangle that we should blit should be, but we can calculate it. So if you comment that out, let's say that we want to clear a rectangle that is about 50 pixels high, perhaps, and let's take a nice and evenly divisible by 16 number, because the Blitter operates in words only. And let's make that width 224. So what you write into the Blitter size register is the width times 64 plus, the height times 64 plus the width in words. So let's call them something better. And let's type them in the correct position. And let's set them to something. The blitter height we already decided would be 50. If we wanted to clear more than one bit plane and the bit planes were interleaved, we could have multiplied this by the number of bit planes that we wanted to clear, but we only have one bit plane. The width in words is 204 divided by 16. So about the blitter height and the blitter width, these occupy 6 bits each. I'm sorry, they occupy 10 bits and 6 bits respectively, where the width can be from 0 to 63, where 0 means 64 words. So you type the actual number of words here, and if it exceeds 63 words, and then you have one last chance, and that is to set it to an even 64 words. For anything wider than that, you need to access the ECS and AGA extra registers for this blitter size. And the height can be 1000, maximum 1024 pixels high. And likewise, if you exceed 1023 in height, then it wraps around to 0, so that 0 means a height of 1024 pixels. We're no danger of hitting these limits with these values, so we're happy with this. Gonna put a little division here. And so that's the last thing you do. What do we need to do before this? Well, we need to point the destination to the screen, right? Because the blitter has 3 source registers, source pointers, to anywhere in chip mem, and 1 destination pointer, which must also be in chip mem, of course. And that is because we're doing this with a custom chip and not the CPU. Only the CPU can access all the memory in the Amiga. So the destination register is quite close to this register in the custom chip register map. We're going to put something into this register here, and if we put screen here, then the blit will be aligned to the top left corner of the screen buffer. We would like to specify a X and Y position perhaps, so let's do that. We need to find some way of adding to this address to center the blit in the middle of the buffer. So we're going to call this blitter X. And we need to calculate what 320, the width of the screen buffer, minus 224 divided by 2 is. And the blitter Y is nominal. Well, you can put anything here. Why not put 48 there? So no, that's confusing. We'll just set a Y value right there. Now we need to know what the byte width is of the bit of each line in the bit plane, and we don't quite know that. We know that it's the width divided by 8 anyway. Everything is specified in bytes. So let's calculate that. Let's do it in steps. And the offset is this value times width divided by 8. We set this constant at the top of the source. And we need to add the X position, which is currently in pixels, also divided by 8. So that's the offset, and we simply add that to the address. Now, what else do we need to do? Well, we need to tell the blitter what operation to perform, and some other things. We'll get to those, but we'll take it in the simplest steps. So the way to do that is to write the blitter control registers. There are 2 of them, 2 word registers, And they're here. Chip memory, custom chip register map. And it consists of a high word and a low word, which looks something like... I'm going to write some strange form of hexadecimal notation here, and explain what the symbols mean. This is what the two words look like. These are 8 nibbles, and you can map them to the operations you want to perform. It enables different things in the Blitter chip. For example, this is the A shift value from 0 to 15. This is the B source shift from 0 to 15. And we know we don't want to shift anything right now, so we can set them to 0. This M is sort of a source mask, 4 bits that tell you which of each of the three sources and 1 destination should be enabled for this Blitter operation. And in our case, only the destination should be enabled. And these 8 bits are the logical combination descriptor. The 8 bits tell the Blitter in each of the 8 possible combinations, in each of the 8 combinations possible with 3 sources, what the destination bit should be. So in our case, we want all the operations to result in a 0. So we type it like this. And this then is a valid Blitter set of Blitter control words. But this is not enough. Hang on. We called this something else, didn't we? Just so we don't get any assembly errors. So, and this has bugged me for a time. Alright, so what else do we need to do? Well, we've defined the memory window size, where it starts in memory, and how to combine the bits and produce some sort of output to it in the Blitter control words. But this is not enough. If we run this, then we'll use whatever so-called modulo value set by some previous blit that we have no idea what it was, unless we blitted it ourselves. So the operating system has made some last blit before us and has left the modulo value at some random value. That means that the modulo, the skipping between rows in the Blitter rectangle here, could be 0, resulting in a not a rectangle at all, but just a stream of words, one after another. Or it could be 32,000, causing our blit to go overwrite some other chip memory. So we need to set that, and that's how we only need to set the destination modulo, and that you do that by writing to this register bltd mod. And what should the value be? Well, we can calculate that. We know that we want to that this is the word width of the operation, and we want to make it skip to the same horizontal position, Blitter X, on the next line on the screen, on the next row in memory, or row in our Blitter window that we're setting up now. So I don't want to call this Blitter mod, BLT mod or anything to conflict with constants that are named the same way. Let's call it skip, and let's calculate it. We know that, and this value is in bytes. It's how many bytes in memory it should skip. So this should always be an even value, and any odd value will be rounded downwards to an even value. So we know that we want to basically take we could do it two ways. We could take the difference in widths and divide it by 8, or do it some other way. I guess this is the simplest. And I made a typo already. Wow. Okay, so this is the Blitter skip, and it should skip something like 14 bytes, maybe, no? Something like that. We'll notice if the modulo is wrong, then our blit will be skewed. So each source and destination have their own modulos, so it's very dynamic. You can combine a 1-bit plane mask with a 3-bit plane bob and blit it onto a 5-bit plane screen if you should like, so that all the sources and the destination have different modulos. But this is not enough. We need to set up the Blitter in 2 steps. One thing that you need to do only once at the start of your demo is to enable Blitter DMA, because after all, even though the operating system likely has it turned on, it could have been turned off by some other process, or maybe if you're making a demo that's loaded by a track loader, it's cleared the Blitter DMA for some reason. So the way to do that is to set bit 6 in DMA-con. You know, the register that controls the Blitter, sprite, copper, etc. DMA channels. And you only need to do this once. Another thing that you need to do always is to wait for the Blitter to finish its last blit before attempting to overwrite the Blitter registers, as we are doing down here. And you do that with a blit wait. A Blitter wait, and this is what it looks like. This is an extra test instruction for compatibility, and then we need to busy wait for a flag. I'm going to type it like this. This is bit 14, also in DMA-con. And as long as it's set to 1, we continue waiting, and when it's cleared, we know that the Blitter has finished its previous job and is ready to receive instructions again. So this is basically it. Let's try it. Anything can happen, but we've succeeded. So that's your first blit. If you want, you could change all the result bits of all possible combinations of the 3 sources to 1 and get a filled rectangle instead. So you've just achieved your first blit on the Amiga. In the next tutorial, we'll take it further. See you then.